All right, so this video is going to cover chapter 1 in the Math 115 for UMA. It's a lot of vocab, so there's probably a lot of talking, but I think we'll be okay. All right, so if we go through statistics, like what is statistics? It's actually a science. We're studying things. So the science of statistics, capital S, is the collection, analysis, interpretation, and presentation of data. So all of those pieces together build statistics. And I say with a capital S because, as you're going to see down here in a little bit, lowercase s is a term within statistics. I don't make the rules, we just have to follow them. So within statistics, some popular important words are data. Data is any set of observations or results of a sampling. Differential statistics is when you're just organizing and summarizing that data. So it could be graphing, it could be tables, it could be finding the averages, it could be percents. Anything that just comes directly from your sample is differential statistics. Inferential statistics are the formal methods used for drawing conclusions. So where you might see them is voter polls, where people are making predictions about elections, or test scores about a whole state based on a sample they're looking at. They're using that sample to say, based on this group, here's what we think about the whole population. And then probability is big in statistics because it's a mathematical tool that studies randomness. So it talks about the likelihood of something occurring or the fairness of an event, but it's never guaranteed. There's always a chance that it couldn't happen, even if it's really, really likely. So those are kind of the big things we're going to talk about, is how to get data, what to do with the data initially, how to bring that to the population, and then how to use probability to tie it all together. So that's the overview of statistics. Now the vocab that we're going to use throughout the entire course. Population is the collection of people or things that you're actually studying, the entire group. So maybe we're talking about UMA as a whole, every single student at UMA. Maybe we're only talking about the math department, but we want to know every single student in the math department. Maybe we're talking about a whole town. Maybe we're talking about a whole state. But you're probably not going to interview every single person. So it's the whole group that you're trying to gather some insight on. The sample is the piece of that population that you're actually talking to. It's the subset. So it's the people you're asking. So maybe for good, bad, or otherwise, if I'm looking at the math department, maybe I ask you guys. We'll talk about whether that's a good sample or not later, but I ask you guys and then I take my results and apply it to the whole math department. You can have good samples, you can have bad samples, but it's just a small group that's part of the population. Here is where our lowercase statistic comes in. A lowercase statistic, lowercase s, is just a number that represents the sample. So it's an average, it's a percent, it's something that has to do directly with the sample. So I remember it because they both have s's. A parameter is a number that you estimate from that statistic and apply it to the population. So I might use the average of my sample to estimate the average of the population. So the statistic is an actual value that you can calculate. The population is something that you estimate using probability. That's the parameter. A representative sample is a group that mirrors the characteristics of the entire population it represents. So if we're talking about all of UMA, our sample needs to have students from all of the majors. If we're talking about the whole math department, we would want students from all of the classes. If we're talking about a state, we want people from all counties. We want all genders. We want all belief systems. We want all, like, whatever characteristics we're looking at, our sample should mirror the actual population. Otherwise, we're not getting a good representation and our numbers might not be valid. A variable is the characteristic you're studying. And that could change. You could look at colors, you could look at ages, you could look at grades, you could look at weights, you could look at heights. It's whatever you're studying in that moment. There's two types of data. Your characteristics often are going to be listed with capital letters, your variables. So you might have a capital X or a capital Y. That's just saying, hey, that's the variable we're paying attention to. They're either going to be numerical, like heights and weights, or categorical, like colors, or I don't know, shoes versus like shoe types, flip-flops and sneakers and dress shoes. Those are just different types of the data that you'll get. So quantitative is your number and qualitative or quality is your categorical. We'll get more into that. And then two of the most popular statistics and parameters we're going to use are the mean and the proportion. The mean is that average term you've heard, add up all the values, divide by the amount of values, and the proportion's the part of the whole, like 5 out of 10, 8 out of 15. So those are vocab words that you're going to use a lot. You'll get very familiar with them, but just be prepared. So let's practice identifying some. All right, so let's look at this example. Determine what key terms refer to. So we want to know the average or mean amount of money first-year college students spend at ABC College. That's our population. All first-year college students at ABC College. On school supplies that do not include books. We randomly surveyed 100 first-year students. That's our sample, the 100 students surveyed. Then 3 of those students spent $150, $200, and $225 respectively. So parameter has to do with the whole population. So we're going to say the average money for the whole first year class. And then the statistic is going to be the average money for the sample, just for those 100 students. The variable, so the piece we're studying, is the money spent. And then the data would be those actual amounts, $150, $200, and $225. So I would pause the video and try this, see how you do. Check back in when you're ready. All right, we want to know the average or mean amount of money spent on school uniforms each year by families with children at Knoll Academy. So that's our population. Families with children at Knoll Academy. We randomly surveyed 100 families. That's our sample. 100 families with kids at the school. 3 families spent $65, $75, and $95. So our parameter is going to be the average money of all families. And then the statistic is the average money of our sample families. The variable we're looking at is the money on uniforms. And then the data would be, for example, 65, 75, and 95. All right, let's look at another one. A study was conducted at a local college to analyze the average cumulative GPA of students who graduated last year. fill in the phrase that best describes each of the terms below. So all students who attended the college. That sounds like a population, but we only care about students who graduated. So let's look if there's one, all students who graduated. So that's F. All students who graduated. So our sample is going to be the selected students. So a group of students who graduated from the college is going to be our sample. So that's D. So we're talking about cumulative GPA. So our statistic talks about the group and the parameter talks about the whole college. So let's look. So average GPA of students who graduated, average GPA of students in the study. So the study tells us that one's the statistic, and then the other one becomes the parameter. And then the variable is what we're looking at. So we're looking at GPA. So that's going to be our variable. And then data are the actual numbers. So that would be C. Why don't you try number 2? Pause the video, see what you can do, and then come back. A survey of athletes in a university was conducted to study the height of athletes in meters. Fill in the letter. So population would be the average in the university. Nope, average is a number. So let's see. Athletes in the university is our population. And then randomly selected athletes is our sample. So now our statistic and our parameter, so that's these two. And then, so the average in the survey is our statistic. The average in the whole university is our parameter. The variable is what we're looking at. So we're looking at height. And then the data are the numbers. So we're looking at G. In both of these examples, they give us like a loop. They say all students who attend the university, all students who attend the college. Those are a population, but we're only looking at students who graduated or athletes. So we're shrinking our population based on the terms of the problem. So that's one thing to pay attention to, is your details. All right, let's do a couple more of these. As part of the study designed to test the safety of electric automobiles, the National Transportation Safety Board collected and reviewed data about the effects of a crash on test dummies. Cars with dummies in the front seat were crashed into walls at a speed of 35 miles per hour. So there's our population, cars with dummies. We want to know the proportion of dummies in the driver's seat that would have head injuries. So we're looking proportion of dummies in the driver's seat. So those are going to be our statistic and our variable. The statistic is just our, not statistic and variable, sorry, statistic and parameter. Statistic is going to be the ones in the study. The parameter is going to be all. Then, let's see, we start with a sample of 75. So that's our sample. And then we kind of look at what we're talking about. So the variable is if they would have head injuries. And then the data on this is just yes or no. Did they or didn't they? So that would be qualitative or categorical data, because we're just saying, did they have it or not? All right. So why don't you pause the video and try this one? All right, a survey is conducted to check the time taken by mobile for charging of battery from 50% to 100%. We want to know the proportion of Android mobiles that are charged to 100% within 30 minutes. So our population is all Android mobiles. And we're looking at, are they charged within 30 minutes? Let's see. We start with a simple random sample of 200 mobiles. So our sample is 200 mobiles. And then we're saying, are they charged or not? So that's yes or no. Now we're going to look at our information. So proportion of charge. So the parameter is the proportion of all that are charged. And the statistic will be the proportion of the sample that are charged. All right, we got two more in this section. Determine what the key for, so same thing. An insurance company would like to determine the proportion of all medical doctors who have been involved in one or more malpractice lawsuits. So population, all medical doctors. And we're trying to find if they've been involved in malpractice lawsuit. How can they answer that question? Yes or no? Okay, the company selects 500 doctors. That's our sample. And asks them if they were or not. So now we do our parameter and our statistic. So the parameter is the proportion of all doctors. Of all, it would help if I could write doctors. And then the sample is the statistic is the proportion of our sample doctors. All right, let's try this last one. Study is to be conducted by a news agency to find the proportion of all truck drivers. So all truck drivers. And then we know these are both proportion. So parameter is proportion of all truck drivers. Statistic is proportion of sample truck drivers. We're looking at if they have no points. So variable, do they have points on their license? Their choice is yes or no. And our sample was 1,000 truck drivers. So the reason we did so many of them was to show you that the order doesn't matter, that you figure them out. Different people's brains are going to see them in different ways and process differently, whether they find it as they read or if they read the whole thing and find it in pieces. It doesn't matter, whatever works for you. So that was 1-1. Let's get a little more specific into our data types. So we kind of talked about qualitative and quantitative before. So the qualitative, those are our categories or descriptions. They're going to be words generally. And then your quantitative are numbers. They're things you get from counting or measuring. They're usually easier to play with and analyze just because you can do a lot more with numbers. And more mathematicians like them better doesn't mean they're necessarily better. Discrete numbers are countable. So you're going to have whole numbers. How many things can you count? If you're talking about people, you can't have half a person, so it would be discrete. Continuous have infinite possibilities. That's where you have your measurement. You can always get smaller. You can go from inches to half inches to quarter inches to eighth inches. You can go from meters to centimeters to millimeters. So you can always get smaller. So your continuous is typically a measurement. So let's kind of look at some of our data here. So is our information discrete or continuous? So the number of books you can carry in your backpack. You're probably not going to have half a book. Still kind of counts as a book. So that's discrete because you can count the number of books. The weight of the backpack. That's a measurement. So that's continuous. Why don't you try the next one? All right. The number of machines in a gym. That's going to be discrete. You can count the number of machines. Even if they're broken, it's still a machine. Area of lawns in square feet. That's a measurement, so that's continuous. All right. You go to the supermarket and purchase 3 cans of soup. They are 19 ounces of tomato bisque, 14.1 ounces of lentil, and 19 ounces of Italian wedding soup. 2 packages of nuts, walnuts and peanuts. 4 different kinds of vegetables, broccoli, cauliflower, spinach, and carrots. And 2 desserts, 16 ounces of pistachio ice cream, 32 ounces of chocolate chip cookies. Name a set that's quantitative and discrete. So we're looking at numbers and countable. So you could say the number of cans of soup. You could say the number of desserts or the number of packages of nuts. That's your discrete and countable. Now, quantitative and continuous, those are our measurements. So that could be the weight of the soup, 19 ounces of soup. It could be the weight of the dessert. And then name a set that's qualitative. So that could be the type of vegetable. It could be the type of dessert. It could be the type of soup. There's not just one answer. It's just about thinking about the different things that they could be. So why don't you pause the video and try this one? All right, name a set that is quantitative and discrete. So we could say the number of types of nails or the number of things. Quantitative and continuous could be the weight of the nails or the weight of the screws or the weight of the oil. And then qualitative could be the kinds of nails or the kinds of screws or the items you're buying. Those are all qualitative. All right, let's look at this. So we're going to determine if it's quantitative or qualitative. And then if it's quantitative, is it discrete or continuous? So number 1, color of backpacks. Colors are words, so it's qualitative. The number of pairs of shoes, so that's a number, that's quantitative. And you have, you count your shoes, so that's going to be discrete. The type of car you drive is a quality. The distance from your house to the nearest grocery store, distance is a number, so that's quantitative. And it's a measurement, so it's continuous. IQ scores, those are numbers, so it's quantitative. And then are they discrete or continuous? So IQ numbers are always whole numbers, so they would be discrete. Good. All right, you try this one. Okay, color of house is qualitative. Number of classes would be quantitative, and you can count them, discrete. Even if you drop one, you still took it. It either doesn't count or it counts, but it doesn't count as half a class. So that it would be discrete. Type of calculator, those are qualitative. So even though, with scientific calculators, you can have a TI-83 and a TI-84 and a TI-89, they have numbers in them, but they really are just qualitative. They're the types. Weights of dogs, so weights are numbers and they're measurements, so it's continuous. And then the number of correct answers on a quiz, it's definitely quantitative. And then this kind of depends. So if they're either right or wrong, it's definitely discrete. If you're talking about points, you either got this many points or that many points, it'd be discrete. But if you're talking about you can be a half right or a quarter right, you could defend continuous on this. But I think this is just saying it's intended to be direct. But you could defend that. All right, let's look at a graph, a pie chart here. So a statistics professor collects information about the classification of her students as first-year students, sophomores, juniors, or seniors. The data she collects are summarized in the pie chart. What type of data does the graph show? So we're just looking at their year in college. The way it's written is words, so this is qualitative data. Pie charts are going to show qualitative data. Even though they might be talking about numbers because of the way they're presented, you're not actually getting numerical data out of them. So pie charts are qualitative. All right, let's look at this one. The registrar at State University keeps records of the number of credit hours students complete each semester. The data is collected and summarized in the histogram. Then it gives you the boundaries. So if we're talking about numbers of credit hours, that's quantitative. And since you can't get half a credit, it's discrete. So that's that information. That kind of leads us into our displays. So when we're trying to display data, percents can be helpful, right? So especially when sample sizes are different. If I did one sample of 20 people and one sample of 50 people, the numbers don't necessarily mean anything, but the percents can help us compare them. Depending on also what we're looking at, different graphs might be nice. So sometimes a pie chart's good because it shows you the proportions of categories. But sometimes a bar graph is good because you're trying to compare numbers. Bar graphs can be vertical or horizontal. There's other ones that we're going to work with, but those are the two that we're going to start talking about. One thing to pay attention to is if people can be in more than one group, sometimes your percents can add up to more than 100. If that's the case, you can't use a pie chart because you can't put more than 100% in that circle. Sometimes they don't add up to 100% because a category is left out or people didn't answer. So you can't use a pie chart unless you add an other or unknown category to make up the difference. So those are just some things to think about with data being displayed. And if you notice a pie chart that doesn't have 100% data, be suspicious of it. Sampling is how you get data. So there's different ways to gather your sample, which we're now going to talk about. You want your sample to be representative. You want it to have the same characteristics as the population. So if I was interviewing a college, if I was interviewing UMA, I would want first years, sophomores, juniors. I would want non-traditional students and students right out of high school. I would want students from every major. I would want students who just are taking random classes instead of being in a major right now. If you don't represent everybody, then your results are going to be wrong and you'll interpret them wrong and make poor decisions. Random sampling, so we're on to the next word here, means every member of the population initially has an equal chance of being selected. So if my population's UMA, a random sample means at least at this moment in time, every student at UMA could be selected. Then there's different types of random samples. A simple random sample is typically considered the easiest. Every member has an equal chance from start to finish. You could put everyone's name in a hat and pick them. You could number everybody from 1 to whatever and use a random number table. You can use a random number table, a random number generator, which I'm going to show you on the calculator. Right? These are all ways to get a simple random sample. So on your graphing calculator, if you hit the math button, which is this button right here, then you're going to come up with a list. And yours is going to look pretty much like this, slightly different, but basically the same. Then you're going to arrow over to the probability menu, the PRB menu. And we're going to go down to number 5, where that says randint. What that means is random integer. Depending on the model, like if you have an older model or a TI-83, your calculator's just going to say this, and you're going to type the min, comma, the max. If you have an 84, a newer version or something higher, it's going to ask you the min and max this way. So you would enter the min, you would enter the max, and then n would give you the amount. So let's say I want to pick 2. Then if you hit enter, it will tell you which ones to pick. If you do it again, you get different 2. We're going to get more into that, but your calculator will do a simple random sample for you. All right, a stratified sample divides the population into groups, then randomly takes a proportionate number from each strata. So strata is the name of the group. So maybe we're going to divide this into departments. We're going to say everyone who's a math major, everyone who's a science major, everyone who's an English major, everyone who's whatever. And then we're going to take a simple random sample from each group. The proportionate part is if the math majors have 100 students, but the science majors only have 50, and we want our sample to mirror that, we need to have twice as many math majors in our sample as science majors. So we don't want them all to be equal if they're not equal in the population. You want your sample to match. That's what that proportionate piece means. Cluster, you're still going to divide them into groups, but instead of taking some people from each group, you're going to pick some groups and then interview the whole thing. So in stratified, you're going to do the departments and then ask some students in each department. Versus cluster, if you did departments, you would ask every student in some departments. And then we're going to find one of each of these shortly. I just want you to kind of get the vocab. All right, systematic. You randomly pick a starting point. So maybe you start at the 10th person. Maybe you start at the 30th person. Maybe you start at the 50th person. And then you take every nth piece of data. So if I start at the 5th person and then ask every 15th person after that, so I would ask the 5th person, plus 15 would be the 20th person, plus 15 would be the 35th person, and I just keep going until I get the number of people I want. If you have a whole list, you can just number the list and do it that way. If you don't have a list, like if I was doing it at a high school, I could stand at the cafeteria door. Everyone's going to lunch. So you stand at that door on the way into the cafeteria and ask. You'll get everybody at some point. So that's systematic. The final sample is not a simple random. This is a convenience sample. It's not random. It's easy to get, often costs less, and it's often biased because if it's easy to get, you're probably leaving somebody out. So for example, if I'm asking about where people buy their shoes and I'm standing outside of the Nike shoe store, I'm going to get different answers than if I'm standing outside Walmart or if I'm standing outside the ASIC shoe store, right? So you want to pay attention to your sample and how they got it. All right. So that's different kinds of samples. Like I said, we're going to get into those in a second. Whenever you're taking samples, you're talking about people. There's always a chance that your sample doesn't work. Somehow, even though you did a great sample, every 15th person just happened to be a math student instead of a science student. So because you're getting samples, you could end up with what's called a sampling error. These are just caused by the fact or by the process of getting samples. The larger the sample, the smaller the chance of a sampling error because you're asking more people. Non-sampling errors are errors caused by anything else. That could be how the person asked the questions. That could be they typed the answers wrong. That could be Something was malfunctioning while they were collecting the data. Just something that didn't have anything to do with who they asked. And then sampling bias is even when you do everything right, your sample isn't representative. So maybe I interviewed 100 people and somehow all 100 of those people ended up being male. I've cut all females out. So even though it wasn't intentional, even though I did everything right, I have a bias eliminating the female's perspective. So therefore, I am making incorrect conclusions based on their perspective. All right, so let's get into some things. How do you evaluate studies based on that information? So if you're given a study and you're looking at that, you want to say, was the sample representative? Bias leads to poor conclusions. So we want to say, did they ask, was it a random sample? Did it represent people? Does it have bias? Those are things you're looking at. Was it a good sample size? Was it big enough to try to limit some of that sampling error? If you ask 2 people, you're probably not going to have a very representative sample. Who asked the questions is important, right? So if someone who has a vested interest in making money off of this is the one who's asking the questions, that might affect who's answering. If my boss were to ask me, do you like your job? I might respond differently than if it was some anonymous person. Okay? Who responded? If people refuse to respond or don't have time to respond, you could end up having a whole chunk of people missing. So you want to pay attention to who answered the question, not just who they asked, but who answered. Who funded the research, right? So if we're trying to research textbook companies and the person like Pearson, who makes a ton of money off textbook, is the one funding the research, you might be suspicious if Pearson wins, right? So you want to pay attention to that. Is the data clearly presented? Is it all there? Is there 100%? Is it clear? Is it easy to see? Those are all things you want to look at. Are all variables considered? So there's this thing called confounding. Sometimes multiple things can go together, right? So if you're going to be doing math online and Pearson is the only one with an online product, is Pearson really the best, or are they just the only one that has the option? That's hard to say. Now that I found my open math, I might actually be able to look at the two. Sometimes if you're looking at like, did TVs in the house cause obesity? Right? TVs in the bedroom cause obesity. Well, did you consider the health and size of the person before the TV was in the bedroom? Or their family? Or if they use the TV? Like, all of those things together can affect the results. So one thing to pay attention to whenever you're looking at a data is all of those little pieces and how they could have an effect on the information. Okay, so now that we've gone over some different things to look at when evaluating, we're going to go through and talk about those samples. So, simple, random, stratified, cluster, systematic, convenience. Those are our choices. So a study is done to determine the average tuition that San Jose State undergrad students pay per semester. Each student in the following samples is asked how much tuition they pay for the fall semester. What type of sampling is done in each case? So look at A. There's 100 students taken by organizing their name by classification. First year, sophomore. So we're putting them in groups. And then we pick 25 from each group. So because we're taking some from each group, that's stratified. Then we look at B. A random number generator is used to select a student from an alphabetical listing. Starting with that student every 50th student is chosen. So as soon as you know it's every 50th, that tells you it's systematic. Okay, C, a completely random method is used to select 75 students. Each person has the same probability of being chosen. That's simple random. D, first year, sophomore, junior, and seniors are numbered 1, 2, 3, and 4. So we're grouping them, group 1, group 2, group 3, group 4. A random number generator is used to pick 2 of those years. All students in those 2 years. So because we're doing all of 2 of the groups, that's a cluster. And then finally, an administrative assistant is asked to stand in front of the library one Wednesday and ask the first 100 undergrad students he encounters. That's convenience. It's just the first ones you see. There's no random to it. So those are the different types of samples. Why don't you pause the video and try this one? Okay, a soccer coach selects 6 players from a group aged 8 to 10, 7 players from a group aged 11 to 12, 3 from a group 13 to 14. So there's a bunch of groups. We take some from each. That is stratified. Pollster interviewed all resource personnel in 5 companies. So there's a bunch of companies. We research all in some. That's cluster. High school researcher interviews 50 teachers and public and 50 private. So we have 2 groups, some from each. That's stratified. Medical researcher interviews every 3rd cancer patient. That tells us systematic. High school counselor uses a computer to generate 50 random numbers and then pick students who correspond. So 50 random is simple random. And then a student interviews classmates in their algebra class. So they just ask the people that were right next to them. That's convenience. All right. Okay, we're going to use this table to make some samples. So each group is, or each row is going to be one of our groups. So these don't count as datas, they're just our groups. So if we're going to create a stratified sample by rows, we're going to pick 3 quiz scores from each row. We're going to use the calculator to help us with that. So we're going to hit the math button. So I'm going to bring up the calculator over here. So the math button's right here. We're going to hit that button. We're going to arrow over to probability. And, oops, I didn't mean to enter. So math, arrow over to probability, and we're going to choose number 5, our random integer. Now, because we want, each row has 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 options. We're going to start at 1, we're going to go up to 10, and we want to pick 3. So 1, 10, 3, hit enter. We get 4, 4, 1. So 4 is 9. And then 4 again is 9, and then 1 is 5. So that's our first set of data. I'm going to hit enter twice, and in row 2, we get 6, 2, and 3. So 9, 10, and 5. Do it again, and we get 9, 6, 5. So that's 8, 9, 9. Do it again for row 4, and I'm just going to keep hitting enter, enter. So 9, 6, 4 is 7, 10, 9. Do it for row 5. We get 9, 10, 5. So 7, 7, 8. Do it again. We get 10, 10, and 6. So truly random data allows for repeats. That's why it's okay that we use the data points twice. Don't worry about that. So this data is what we would use for our stratified sample. We can use the same thing for our cluster sample. The difference is we're going to pick a row and use the whole row. So this time, when we do our math prob, bring up our calculator, math over to prob, choose number 5. We have 1 row to 6 rows. and we want to choose 2 rows. So those 2 rows are row 2 and row 4. So row 2 gives us this data: 7, 5, 10, 10, 8, 9, 7, 8, 7, 8. And row 4 gives us this data: 9, 8, 6, 9, 5, 10, 9, 10, 7, 9. So that data is different. It's even a different amount of points, but it's still a random sample based on that table. A simple random sample, we're going to just number these from 1 to 60. So we're going to label this 0 through 10, or 1 through 10, and then 10 through 20, and so on. That's just going to help me find them, whereas this is 60. So 15 quiz scores. So there's 60 data points. So math over to Prob 5. We're going to start at 1. We're going to go up to 60, and we want 15 scores. So these are our numbers. So the first score is 50. So 50 is right here. That's 8. And then 42, 7, 6, 47, 4, 43, 45, 22, 45 again. So we're just going to use that one again. That's okay. 23, 22, 32, 21. You might have to use your arrows to go over, and then 57. So those would be our data points. Okay, for our systematic sample, we're going to do like every 9th. So if we go in and we do math, arrow over probability, choose number 5. We have 60 numbers. We're going to randomly start at number 16. So number 16 is right here. So that's 9. And then we're going to do every 9th. So 1, 2, 3, 4, 5, 6, 7, 8, 9. 1, 2, 3, 4, 5, 6, 7, 8, 9. 1, 2, 3, 4, 5, 6, 7, 8, 9. 1, 2, 3, 4, 5, 6, 7, 8, 9. 1, 2, 3, 4, 5, 6, 7, 8. And then we just go back to the beginning. 9. And then keep going. 1, 2, 3, 4, 5, 6, 7, 8, 9. How many do we have? That's 3, 6, that's 7. 1, 2, 3, 4, 5, 6, 7, 8, 9. 1, 2, 3, 4, 5, 6, 7, 8, 9. 1, 2, 3, 4, 5, 6, 7, 8, 9. 10. 1, 2, 3, 4, 5, 6, 7, 8, 9. And then 1, 2, 3, 4, 5, 6, 7, 8, 9. And then that would be our data set with the systematic. So you randomly start somewhere and then count every other. Now, even though they erased on here at one point, why did we get different samples in each one? Well, they're all random. So they're going to start in different places, go different ways. They're all based on different things. If I did this again, I would start in a different place. That's the benefit of doing samples, is that randomness is going to create them so they're all different. But each of these data sets looks pretty similar in what we're getting. So that's kind of how you get each sample. All right, let's look at another question here. Suppose ABC College has 10,000 part-time students. This is the population, the 10,000 part-time students. We are interested in the average amount of money a part-time student spends on books. Asking all 10,000 students is almost an impossible task. Suppose we take 2 different samples. It's unlikely that any student is in both samples. All right. So first, our first sample is that we use convenient sampling and survey 10 students from a first-term organic chemistry class. Many of these students are also taking calculus in addition to organic chemistry. The amount of money they spend is as follows, and it's these numbers. The second sample is a list of senior citizens taking PE and asking every fifth senior on the list. They spend this much money. Do you think either of these are representative samples? Now, if we think about it, they're probably not. The first sample is looking at kids that are taking science. Science textbooks cost a lot of money. And a lot of them are also taking calculus. Math textbooks can cost a lot of money. So the first sample, A, is convenience. As soon as it's convenience, it's probably not representative. And then science and math cost more. Then we look at the second sample. We're only looking at PE. Those textbooks, if there are even ones, are a lot cheaper. So those are going to cost less. So you're looking at vast differences of the scale. So no, neither of them are really representative. Since they're representative, is it wise to use them? No. Anytime it's not representative, you're not getting good information, so it's not a good idea to use them. And then, is the sample biased? Yeah, they're both biased towards whichever group. Neither of them are going to have accurate data because they don't have a good cross of all of the students in the 10,000 group we're looking at. All right, so why don't you try this one and pause the video and then come back. A local radio station has a fan base of 20,000 listeners. That's our population. They want to know if the audience would prefer more music or more talk shows. Asking all 20,000 listeners is almost impossible. The station uses convenient sampling, that's a hint right there, and surveys the first 200 people they meet at a music event. 24 people prefer talk shows, 176 people prefer music. Do you think this is representative? So the answer is no. And the reason it's probably not representative is because they're at a music event. If they were just at a random event, it'd be a whole different story. But because it's a music event, people are more likely to prefer music. And because it's convenient, it's probably not representative. So those are the things we're thinking about. We kind of hinted at this in the last one, our variation in our data, but there's changes in the measurement. So if you buy a packed case of soda, every can is not going to have the exact same amount of soda. There's usually a range of guidelines. They're all going to be pretty close, but they might be a little bit different. Sometimes when you're asking questions, people are estimating or rounding. So those are going to change the answers you get. So that's another reason why sometimes your data might be different depending on the sample, is just because things are different. Machines do things different. Different people have different answers. The smaller the sample size, the more variation. So those are kind of things to keep in mind as well. So that is the end of 1.2. Okay, section 1.3 is going to talk about frequency tables, and levels of measurement. So our rounding guidelines that we're going to carry throughout statistics is always use one more decimal place than in the original data until you're done. And if possible, only round at the end. Fractions are okay unless it tells you to do something different. So for example, if your data points are 2.5, 3.6, 4.2, if you start working with something, you're going to carry 2 decimal places until the very end and then go back down to 1. That just helps preserve the data. So our data has different levels. So those levels look at different specificity. So it's different pieces of how specific you get. So the lowest level is nominal. Nominal data is qualitative. You're just naming things. Colors, types of shoes, things like that. There's no order to them. Ordinal is still qualitative, but now order matters. you can't measure the difference between places. So maybe we're talking about winners of a race, first, second, third, fourth. You know what order they came in, but you don't know how much faster the first place person was than the second place person, and so on. So that's ordinal. Then we get into our quantitative measures. Interval is our first quantitative measure. This, you can measure the difference in numbers. There's no starting point, so that means negatives are okay. So temperature is an interval. You can have negative temperature. Data can be compared in amount, but not using division. So you can say it's -5 degrees, or it can be 30 degrees, but we don't say it's like 6 times as hot. We just say it's 30 degrees warmer. Ratio is when you compare using that division. We're still quantitative. This one starts at 0. So you have no negative numbers in ratio measurement. And this is when you can be compared using division. Frequency is the number of times a value occurs. Relative frequency is the fraction or proportion or percent of the number of times a value occurs. So if we were going to take this data set over here and make a frequency distribution, that just means we're going to go through and figure out how many times each data is in there. So the number 2 happens 3 times. So the frequency is 3. The number 3 happens 1, 2, 3, 4, 5 times. The number 4 happens 1, 2, 3 times. Sorry. The number 5 happens 1, 2, 3, 4, 5, 6 times. The number 6 happens twice, and the number 7 happens once. So those are all the frequencies. If we add those up, we get a total of 20. So to find the relative frequency, we do the proportion or the fraction. So for 2, it would be 3 out of 20, 3 divided by 20, which is 0.15. For 3, we would do 5 out of 20. So that would be 0.25. We already know 3 is 0.15. 6 out of 20 would be 0.30. 2 out of 20 is going to be 0.10. And 1 out of 20 is going to be 0.05. So now we have relative frequency and frequencies listed. Once we have a table, we can use that to answer information. So on this table, we have ranges of heights, how many heights fall in that range, and then the proportion of heights that fall in that range. So we're going to find the percentage of heights that are less than 65.95 inches. So on here, 65.95 appears right here. So everything less than that is going to be part of that percent. So we would add those up. So 0.05 plus 0.03 plus 0.15 gives us 0.23. And to turn that into a percent, we get 23%. If we do between 61.95 and 65.95, we're going to start at 61 and end at 65.95. So we're going to add these two percents. So 0.03 plus 0.15 gives us 0.18 or 18%. All right, let's look at the next one. We're going from 67.95 to 71.95. So 67 to 71 are these two rows. So we're going to do 0.17 plus 0.12, which is 0.29 or 29%. All right, if we look at the next one, we're doing 67.95 to 73.95. So 67 to 73. So that's going to be these three columns. So 0.17 plus 0.12 plus 0.07 gives us 0.36 or 36%. Let's see, the percentage of heights that are more than 65.95. So start at 65.95 and we're going to add everything above it. So we've got 0.40, 0.17, 0.12, 0.07, 0.01, and that adds up to 0.77, which is 77%. All right, now let's look at question F. Question F switches to the number of players in the sample between 61.95 and 71.95. So when we're looking at the number of players, we want just the regular frequency. So we're going to add those numbers. 3 plus 15 plus 40 plus 17 plus 12 gives us 87. So what kind of data are the heights? So we're going back. Heights are numbers, so we're quantitative, and they're measurements, so we're continuous. Now the next one is describe how you could gather this data so that it would be characteristic of all semi-professional soccer players. So one thing you could do is get a roster from every team and take a couple people from each team. We could get rosters of every team, do a random sample of 3 teams and ask everybody. We could get all the rosters and just pick 100 people. There's just a bunch of different ways. You just would pick one of them. All right, so I would suggest pausing the video and trying to answer these questions. All right, so percentage less than 9 is going to be these 3 together. So 0.12 plus 0.14 plus 0.3 ends up being 0.56 or 56%. Between 6.99 and 13.05 is these 3. So we add these. 0.30 plus 0.16 plus 0.18 is 0.64 or 64%. All right, let's see. What's next? The number of towns between 295 and 901. So we're going to add these. 6 plus 7 plus 15 is 28. And then the fraction of towns between 1103 and 1305, that fraction is 9 out of 50. All right, so here's another way to do this. 19 people are asked how many miles to the nearest mile they commute to work. Here's the data. So we're going to look at this and we're going to make a table. So same idea as before. I'm just going to make tally marks as I go. So 2, 5, 7, 3, 2, 10, 18, 15, 20, 7, 10, 18, 5, 12, 13, 12, 4, 5, 10. So I just made tally marks while I crossed them out. And I'm going to turn those into frequencies. So 211, 323, 211, 21. We know that's 19. So the relative frequency, 2 out of 19 rounds to 0.11. 1 out of 19 is 0.05. So we already know that. 3 out of 19 is 0.16. We already know the 2. We already know the 3. We already know the 2. We already know the 1. Now, if I add these all up, I end up with 1.01. Why is it okay that these are above 100%? It's just because we rounded. Sometimes when we're rounding, things add up over that, and that's okay. But those are your frequency and relative frequency pieces. All right, 1.4 looks into experimental designs. So we're going to start going into actual experiments and how those kind of work and the vocab that goes along with those. So the purpose of an experiment is to investigate the relationship between different variables. And with an experiment, because you're controlling things, you can actually look at cause and effect sometimes. So the explanatory variable is what you're looking for as your cause. The response variable is the effect. So for example, maybe we're looking for, does sun cause cancer? Too much sun exposure cause cancer. The cause is your sun, the effect is your cancer. Treatments are different values of that explanatory variable. So different values of explanatory. So that would be like an hour of day in the sun, 3 hours a day in the sun, no time in the sun. Those would all be different treatments. The experimental unit is the person or thing being studied. So the person that you're looking at if they got cancer. Lurking variables are additional variables or additional things that could be affecting your study. So, for example, if we're looking at the sun, but people we're looking at also go tanning, then that could be a lurking variable. Or someone who's older, their age could have an effect on it. Their health, all of those things could also affect whether they're getting cancer. Okay. Random assignment, by like randomly putting in people in different treatment groups, helps spread out those lurking variables to try to minimize their effect. A control group either gets no treatment to try to see what the difference is, no treatment, or they get a placebo, or they get like the current standard. So if we're trying to treat someone for cancer, we're not going to give them no treatment. The control group in that group is going to get what the current standard is for that treatment. A placebo is like no actual treatment. So it might be like a sugar pill that has actual no medicine in it. It helps avoid like the power of suggestion. If you've heard about like a placebo effect, my favorite example is a Band-Aid. When you have a little kid that hurts their finger, and then they come up to you and go, oh, my finger hurts, I want a Band-Aid. And then they put a Band-Aid on and their finger feels better. The Band-Aid doesn't actually make their finger feel better. The Band-Aid stops it from bleeding. But they think the Band-Aid makes it feel better, so that's the placebo effect. That's a real thing in their head. They do that. So in order to take out that power for suggestion and that placebo effect, oftentimes there'll be a control group that gets no treatment, even though they take a sugar pill, to try to see if that's actually making a difference. One thing they do is called blinding. So blinding is a masking that helps prevent that. So a single blind study is when the receiver, so the person getting the treatment, doesn't know what they're getting. They don't know if they're getting the placebo or the regular. A double blind, the receiver and the giver don't know. So the person giving them the medicine and the receiver doesn't know. They're just giving them a certain number. Someone somewhere knows. Excuse me. Obviously, or they can't train it. But those two people aren't involved. So those are different kinds of studies. All right, let's look at an example. Researchers want to investigate whether taking aspirin regularly reduces the risk of a heart attack. 400 people between the ages of 50 and 84 are recruited as participants. The people are divided randomly into two groups. One group will take aspirin, the other group will take a placebo. Each person takes one pill a day for 3 years, but they don't know which one they're taking. At the end of the study, they count the number of people who've had a heart attack. So our population is everybody in the ages 50 to 80. All people 50 to 84. The sample is those 400 people in our study. The experimental unit is each person in our study. Each person's a unit. The explanatory variable, so what are we looking at, is does aspirin, I don't know how to spell it, aspirin, reduce heart attack? That's what we're looking at. Oh, so the explanatory variable is the aspirin. The response is the heart attack. Does aspirin reduce heart attack? And then the treatments, the two options are they're taking aspirin or they're taking a placebo. That's how that vocab goes. Why don't you pause it and try one? Study needs to be conducted on 3 medicines. The height of adults aged 30 to 45. So there's our population. All adults 30 to 45. 90 adults were selected randomly. So that's our sample. 90 adults. And our units are each adult. Divided into 3 groups. The first group was asked to take medicine A for 6 months. The second group was asked to take medicine B for 6 months. The third group was asked to take medicine C for 6 months. Those are our treatments, A, B, and C. The average change in height in each group is calculated. So the explanatory variable is the medicine. The response is the height. All right, let's look at another example. The Smell and Taste Treatment and Research Foundation conducted a study to investigate whether smell can affect learning. Subjects completed mazes multiple times while wearing masks. They completed the paper and pencil mazes 3 times wearing floral scented masks and 3 times with unscented masks. Participants were assigned at random to wear the floral masks during the first 3 trials or during the last 3 trials. For each trial, the researchers recorded the time it took to complete the maze and the subject's impression of the mask scent, positive, negative, or neutral. So, explanatory and response variables. So they're looking at, does the scent, so our explanatory variable is the smell, and the response would be the time it took to do the maze. Time to do maze. What are the treatments? So they had a floral mask, and then they had a no scent mask. So lurking variables. What are some other things that could affect this study? So maybe people's IQ, like if they're really good at mazes or really bad at mazes. Maybe if they have an allergy to scent or to flowers. Maybe if they do mazes all the time. There are all kinds of things that could. These are just some examples. Is it possible to use blinding? So on the subjects, not really. They're going to know if they are smelling a scent or not. But for the researcher, so the person doing the timing, yes, they may not know which mask the person is wearing. So in one way they could, but not in another. So why don't you pause the video and try this one? The placebo research group conducted a study to find the extent of placebo effects. A group of men randomly selected were asked to take a test before and after taking a pill that induces a mild headache. The pill in half of the randomly selected men was replaced with a similar pill that had no effect. For each trial, researchers recorded the change in time men took to complete the tests before and after taking the pill. Describe explanatory and response variable. So the explanatory variable would be the pill, and then the response would be the time to take the test. And then the treatments were the pill that causes headache, and then the pill that doesn't. So the other pill. Lurking variables. So you could have a reaction to pain. Maybe some people have a really bad reaction to headache, so even a mild one's bad. Maybe the test content. Someone's really good at whatever the test is, or someone's really bad. Or maybe they have test anxiety, and it doesn't matter what kind of headache they have, it's not going to help. These are just some. Is it possible to use blinding? Yes. If the pills are the same, there's no way to know which one you're taking unless someone tells you. All right, let's look at example 3. A researcher wants to study the effects of the birth order on personality. Explain why this study could not be conducted as a randomized experiment. What is the main problem in the study that cannot be designed as a randomized experiment? So if we're studying birth order, there is no way to randomly assign birth order. You were either born first, second, third. That it is what it is. So since you can't randomly assign that, you can't have this be a randomized experiment. All right. So why don't you pause the video and try this one? You're concerned about the effects of driving on performance, of texting on driving performance. Design a study to test the response time of drivers while texting and while driving only. How many seconds does it take for a driver to respond when the leading car hits the brakes? So describe your explanatory variable and response. So the explanatory variable is texting while driving. The response is how many seconds does it take to hit the brakes? So time to respond. The treatments are texting and driving only. So texting while driving and driving only. What should you consider? So age, how long they've been driving, accident history. Let's see, maybe the phone type they're using. There's lots of things that you should consider when you're dealing with all of this. Those are just some. Your research partner wants to divide participants randomly into 2 groups, one to drive without distraction and one to text and drive simultaneously. Is this a good idea? Why or why not? So part of it's good because it's random. We like that idea. And if you have enough people, you're going to cancel out some of those lurking variables. But the other part is everybody reacts differently. So many people have different things. It might be better to compare each person to each other. Like, does this person go faster with the texting and without? I, in general, might have a different reaction time than the person next to me. So it's hard to say without knowing more details. So it could be good. It could be bad. Need more information. What are some lurking variables? So maybe how bright the lights are. Bright brake lights might affect me differently. What people are talking about in the texts. Sight issues. Some people may react differently to light versus sound. I don't know. Let's see. How can blinding be used? So someone obviously knows if they're texting or not. But what could be different is if the researcher, the person doing the timing, doesn't know. which they're doing, that could be different. So that could be one way to do that. All right, let's talk ethics. So data's all kinds of things. You've heard before, you can make data say anything you want. Ethics comes in two ways. Ethics comes in presenting your data, and it also comes in gathering your data. So when you're presenting your data, you don't want to falsify it. You want to make sure you're collecting it in proper methods and collecting enough data that it's realistic. It's better that your data proves your hypothesis wrong than you have bad data. Maybe you're doing some collecting and you realize how you're collecting it is bad, so you need to change how you collect it. Report that in the information. So I had to get my doctorate, I had to do research. And I started by collecting some data in notebooks. And I realized, you know what, these kids aren't going to turn these in, they're going to forget. So I started having them do things online. In my dissertation, I wrote about that change. And so because I recorded that change and made note of it, I explained the difference so people could see that. Part of it, when you're doing research on people, you want to make sure they're okay. So when you're doing research at universities, when you're studying people, they have something called institutional review boards. Those boards have to approve research before you can do it. So when I was doing my dissertation, I had to design this research experiment, and an IRB had to approve that it was okay to do what I said I was going to do before I could even start. In any experiment, your goal is to minimize risk. So anything you want to do, you want to minimize risk. Before I mentioned, like if we're doing a cancer treatment study, I'm not going to not treat the cancer. That's why in that kind of a study, the control group is the standard treatment and not no treatment. You also want to get informed consent. A big part about that is it needs to be in writing. People need to be able to understand the consent. They can't just sign something. They have to be able to understand what they're consenting to. Data needs to be guarded. You need to be able to remove identification. You need to be able to share what happens to data after the study. So when I was doing my study on high school students, their parents had to sign. The kids couldn't because they weren't 18. So they signed, but their parents also signed. And in that consent, it said, a year after the study, this data will be destroyed. And then I had to shred it all a year later. All of that is part of the ethics of data collection. So let's look at some ethics here. Describe unethical behavior in each example. Explain how it could impact the reliability and how it could be corrected. So here, a researcher is collecting data in a community. So they're selecting a block where they're comfortable walking because they know many of the people. So it could be okay, but it's not as random because they're choosing it for a reason versus just randomly selecting the block. They're comfortable there, so they're probably avoiding something else somewhere else, meaning they're not representative. And as soon as you're cutting something else out, now you have a biased sample. So to fix the problem, you should randomly be choosing a neighborhood or certain houses in a neighborhood. While they're walking, no one seems to be home at 4 houses on the route. They do not record the addresses and do not return later to find those residents. So if they recorded the addresses and came back later when they were home, problem solved. By not doing that, if they're going during the day and those 4 people were the only families where people worked, you're omitting that whole family. You're omitting that whole group of people. So by actively not recording the information and not trying to follow up, you're purposefully taking those people out, which is unethical, and you're also creating a bias. Okay? C, the researcher skips 4 houses because they're running late for an appointment. When they get home, they fill in the forms by selecting random answers from other residents in the neighborhood. Never, ever, ever, ever falsify data. So bad. It creates bias. As soon as you skip people, you're omitting them. You're not getting your full sample. And anytime you create false data, it negates your study. All right, you try this one. Same thing. So, study is commissioned to determine the favorite brand of juice among teens in California. So, it's commissioned by the seller of a popular brand of apple juice. So, this is a biased interest. So, if the seller of the juice obviously wants people to like their juice, so it's automatically indicating a poor or like a biased thing. If people know they're the ones paying for it, if they're in the study, it might influence their answers. So it's better to have an outside source paying for this. B, there's only 2 types of juice included, apple juice and cranberry juice. So by having such a limited choice, it makes it harder to get a real choice. Like if people only like grape juice, that's limiting everybody that only likes grape juice. This one's not necessarily unethical, but it eliminates a lot of choices. So I would add more. C, researchers allow participants to see the brand of juice as the samples are poured. As soon as they're seeing the brand, you have 2 things. 1, brand loyalty is a thing. If people know in their head that they like a brand, sometimes even if they don't actually like it better, they might think they do just because they like the brand, and so they're going to choose it anyway. It's like the placebo effect. Like seeing the name makes them think it's better. So that's one thing. If they know who's running the study, they might pick it just to try to make the people happy. So as soon as you see that brand, it's skewing the data. So the best way to fix that is to have everything be blind. Sample A, sample B, period. All right, 25% of participants prefer brand X. So X is 25%. 33% prefer brand Y. And 42% have no preference. Brand X references the study in a commercial saying, most teens like brand X as much or more than brand Y. So technically, they're not lying because they're putting those 2 together, and as much or more, like that's not wrong, but it's not true. More people like brand X or brand Y, clearly, and then no preference doesn't mean they like X better. So they're misleading people. That's unethical. They're using the data in their way to say what they want. So again, not lying, but they're not telling the true story. They're not giving the accurate picture. So to do that, they could say most people don't have a preference. They could say that, or they just don't say anything. Those are kind of the things with the ethics. Like, they're not wrong, but it's not okay to say that. Like, those are the things you want to pay attention to. So that is our intro to statistics. That's chapter 1. Let me know if you have any questions.